Hello, everybody. My cat is immediately here and wants to say hi, and I'm like, no, go away. Yep, there she is, right there. Say hi. Say hi. Yeah, there you go. I don't know if you can hear. Welcome back to Chem 140. We are going to do actual chemistry today. I know, amazing, right? Like, what the hell have we been doing the first 3 weeks? Well, it's all like the sort of prep groundwork stuff. That is important for when we get to the end of the quarter. She's just going to keep meowing, so if you hear her in the background, that's her. Huh, Maya? Meow. So now we're going to start putting down the foundation for the more conceptual side of chemistry. So, like, we're going to put our calculator away and not touch it until, like, week 7. Which, for a lot of people, is going to be, oh, relief. And for some people, they'll be like, oh, man, I really like the math part. And, like, yeah, we sort of bounce back and forth between the two in this class. Just some administrivia stuff. Last call for quiz 2 is tonight. I'm going to assign lab 2 tomorrow during the lab Q&A. Lab number 2 is actually very math related, so you'll have to get your calculator back out for that. But Maya, please. I'm trying to teach. Stop that. Maya. Ugh. My goodness. We'll do lab number 2 tomorrow. It is a density-related assignment. We'll talk about what you need to do, but it does involve a lot of calculations. But other than that, we're not really going to do much calculations until we get to, I want to say unit, I had the list somewhere. It's like the unit 11 or something. If you were reading the chat before class, you probably saw that I was talking about quiz number 2. Again, the deadline will be tonight. I will make an announcement for last call and then close the quiz down at some point. I've gotten a lot of emails this weekend, and I mean like a lot, from students that have had questions like, hey, why am I not doing well on these assignments? Or can you help me go over the answer? And unfortunately, the same reply that I have to send to everybody is, I can't talk about the quiz until the quiz is closed. And if you needed, like, hey, what are general study advice? Like, we went over that in the first lecture, so I sent an email that said that. So if you got that message, that was because you were one of many people that asked about it. Please do ask me questions about your quiz, and I think Maya just left. That's good. Please do ask me questions about your quiz after last call, or after it is closed. So when I make last call about an hour later, I will then close the quiz. You'll see the key, and then you'll see the answers, but the answers don't really tell you much. It'll just say, like, oh, your answer was 4.8. The correct answer was 8.3. And that doesn't really help you terribly much. I can say that for every student that emailed me with, I did poorly on the quiz, what am I doing wrong? I went and looked, and I immediately saw what you were doing wrong. They were things like, oh, you gave me an answer that was in the wrong units because you didn't see I wanted gallons. Or you didn't use this number correctly. Or multiplication is hard. Like, things like that. And so, you guys can do this, but with how Canvas works out, I can't give partial credit on those problems. So it's all or nothing. And in life, it's going to be all or nothing. You only get one chance to launch the space shuttle. If you tell it to land at this coordinate and you put it in meters instead of feet, boom. And that has happened before, believe it or not. Discord link. Hold on. Where is the correct email for that? Here we go. Discord. So when students ask for the Discord server link and people try and post it, it doesn't seem to work. But somebody sent it to me. I think it's right here. Yeah, here we go. So I have to post it. So there's the class Discord right there. Let me get you on the lecture preview here. I'm not in that server again. So just keep that in mind. If you're going to ask questions to your peers, like, that's fine. But if you're going in there with the intent of asking me questions, obviously I won't see them. So please do email me questions. And if you have your work available, take a photograph of it and send it to me, and then I can very easily find your answer. Because I actually have all my work written out, too, on my paper. I actually solve all the problems. No, I can't join your server. I'm sorry. That's a conflict of interest. I could join it after the quarter. Well, you know, when I'm not your instructor. Although if you're taking 161 next quarter, I might be your instructor. So... All right, let's talk about polyatomic ions. This is something that's going to come up in Unit 9. Very, very, very important. I put this list in Unit 6 or in an earlier chapter for my classes because we use these a little bit, and then later on when we get to Unit 9, 10, 11, and further, we start to use them a lot. Now, I also put them in here because if this were a face-to-face class, you would be tasked with memorizing these. But because it's not, you don't have to. So you do not need to commit these to memory because there's no way I can enforce that. Like, let's be pragmatic. But in a face-to-face setting, and some classes will slowly start to go back to face-to-face, is my understanding. You are going to want to know these, and you'll be expected to have memorized them. Okay? We're not going to use them for probably another week or two. It'll be after exam number 1 where we actually start to use these a lot. Okay. Importantly, the text that is used in this class, which is the little workbook, I don't know if it has a list of polyatomic ions in there. I give you a separate list. Here's that list right here. It's actually 2 pages, so just before you freak out. And you can pause the video or hit print screen and then send it to your printer. I don't know, whatever you want to do. To have these handy, but make sure that you know where this list is so that you can refer to it when you need it. Because when we get to naming stuff, you're going to want to have these ions handy so that you can refer to them. Of course, if you just memorize them, then you're in good shape, and then you don't have to refer to anything. But I do realize that that is not something that I can enforce in this sort of modality. Now, what the heck are these things right here? So, oh, I don't have my tablet. Hold on. Let me get that so I can draw all over the screen here. So what are these substances? Okay, so here we have, oops, that's the wrong pen. Here we've got a name, and here we have a formula of an ion. An ion just means it has a charge. We're going to talk about that later on. When you memorize or refer to these formulas, you're going to have the formula itself and also the charge. And you need to know both pieces. So knowing that acetate is C2H3O2 isn't enough. You got to know that it's C2H3O2 with a -1 charge. What do the charges mean? What do the formulas mean? We'll talk about that. That's what Chapter 6 is about, and also Chapter 7 and 8 and 9. All right. So that's page 1. Here's page 2. There are some patterns in remembering these. For example, you'll notice that all of these have very similar endings. And some of them have prefixes. For instance, anything that ends in ate or ite and has a hypo, the difference between ate and ite is 1 oxygen. The difference between hypoite and ite is 1 oxygen. And then the difference between ate and per-ate is 1 oxygen as well. Oh my goodness, there are so many jokes. Like, for example, sodium hypobromite. We could talk about that all day, but nah, bro. I could keep going and talk about noble gases, but all the good jokes about them are gone. Like, it just never ends. Don't even get me started here. Alright, so that's the list of polyatomic ions. There's my hint about oxygen and 8-ite endings. If this were a in-person class, I would say, like, make flashcards, test each other, do like an hour of this practice with each other, at least an hour or 2 per week. Like, I don't know, 15 minutes a day is probably good. And before you know it, you will know these. It's just like anything. You have to just get into the habit and the repetition. If you're taking a Spanish class, the way to learn vocabulary is to use it. You don't just look at the chart and be like, okay, I know it. Like, you have to actually try and apply it. And since it's hard to apply this stuff, the best thing you can do is just try and accelerate that rote memorization by just testing each other. Alright, let's talk about matter. Why does matter matter? Well, it makes up everything around us, so we care about it. So what we're going to do is we're going to explore what it can do, such as what states we observe it in. We're going to talk about how we can categorize it, and then we're going to talk about how we can express matter in terms of just writing stuff on a piece of paper. Because all the matter around us has an identity, and we need to identify what the matter is and then give it an identity on paper so that other people will recognize, like, oh, that's iridium. Okay, that's what that means. Oh, that's oxygen. Okay, I understand. That sort of thing. That said, this is a pretty straightforward chapter, but there is a lot of information and details that you will need to know and practice. So, let's get started on that. In this class, we're going to keep it simple. We are only going to look at the 3 common states of matter. And the reason for that is because there are more states of matter than solid, liquid, and gas. They are much more difficult to define with the information that we have at present. We're going to define these states in terms of molecular motion. First of all, we need to define what matter is. Matter is something that both occupies space and has mass. What is space? Space is the region that you take up. For example, if you stand up and you bonk into your chair, the reason that you don't just pass through the chair is because you occupy that space, and if you try and take up the same space as the chair, you and the chair collide and bounce apart. I don't pass through the floor and fall into the person's apartment below me, because the floor occupies space and I occupy space, and those two spaces cannot coexist at the same time. What is mass? This is just the stuff that you are made of. It is the material component that makes up any object. So, for instance, the water in my mug right here is made of something that we put together, and that gives it the identity of what water is. Now, you all know that that's H2O, or you probably know that anyway. What is it? What do we mean by H and then O, and what do those mean physically, and what's inside those atoms, and so on and so forth? That's the point of chapters 6 and 7. Okay, so you can think of matter as anything that is made of stuff, and also as a volume. Some things do not have a volume. For example, sound. Sound does not have a volume. Heat does not have a volume. Light does not have a volume. So those things aren't matter. In fact, those are energy. Energy and matter are related, but for the purposes of this class, we're going to focus on matter. We're going to explore energy a little bit more in 161. These are the three states of matter that we will concern ourselves about: solid, liquid, and gas. Now, you might have some understanding of how these phases behave, but we're going to draw a picture of it in just a second. Now, there is another state that's also common, a plasma. For example, the sun is a plasma. It's an ionized gas. In case that comes up later on at trivia night, there you go. But we're not going to use plasmas in this class. Now, why do we care about phases of matter? Well, we care about matter in general because the whole point of chemistry is to observe how matter interacts with other matter. You did this in lab number 1. I gave you some chemicals, you poured them into each other, and something may or may not have happened. And I realized somebody asked about when is the lab going to be graded, and I forgot to answer that. It'll be graded when it's done. I'm in the middle of working on it right now, but I have to grade all of them, and I have 120 of them before I can upload them. So I can't upload section A before I finish everybody else, because that would not be fair to the people in section S. So chemistry is the study of how matter uploads. No, that's not how that works. Chemistry is the study of how matter interacts with other matter, or maybe how it doesn't interact. For example, when you sit on your chair, the matter of your clothing does not interact with the matter of the seat. That's by design. We would not want a chemical reaction to occur every time you sat down. On the other hand, sometimes you do want a chemical reaction to occur. So if you put Alka-Seltzer in water and then drink that, the substance that is in the Alka-Seltzer reacts with your stomach acid and neutralizes it. So we basically study chemistry to try and identify things that we can and cannot manipulate. I'm going to go to this screen real quick before I do this table. Let me put this on the screen so you can see it. We'll just put it in the middle here. That didn't quite work. There we go. Let me hide that so that I can see the picture I'm drawing. Yeah, that's good. Okay. I need black, and I need a brighter color. There we go. I accidentally overwrote that pink, and I kind of wanted it. That's okay. All right, so what we're going to do is I'm going to make a container. And inside that container, I'm going to put atoms of solid. And what the atoms of solid will do is they will organize themselves in a very regular pattern. Like that. For each of the particles that are in the solid, They're kind of stuck there. Now, this will be due to a force that we're going to talk about later called bonding. But for now, you can think of all of these atoms as they're just kind of tethered to each other. And they're tethered pretty tightly. They can wiggle, but they can't move apart. That's what a solid is. Now, if I had a liquid, it was a little... Shoot. Oh, my undo feature is not working. Okay. There we go. For a liquid, all the particles are close together. However, you'll notice that they are not in any sort of regular arrangement. I'm good at drawing. Thank you. It takes a lot of talent to draw 3 lines and a bunch of circles. Let's see here. Where was I? So these particles... Oops, let me change the color here. These particles do not have a regular arrangement, so they have a random arrangement. They also have a lot of ability to move around. So whereas in this situation, my molecules could only really just vibrate in place, in this situation, they can all move in any direction that they want to. This gives liquids their characteristic that they flow. So if you hold your bottle of water when it's closed sideways, all the water flows towards the top of the container and then settles on whatever side is pointed down. And as you spin your container around, the liquids will move because it can freely do that. With a solid, all you would do is rotate this shape around. The solid would remain in its fixed shape, which we'll talk about in a little bit. Finally, for a gas... Ooh. Sorry, I forgot. I had tilted my pad sideways so that I could draw or write a little more effectively. For a gas, and actually for a gas, we need to do this part. Gas particles will bounce all over the place, but are very far apart from each other. So they are spaced apart. They have extremely low density. And their velocity is incredibly fast. So we're talking about meters per second speeds. So this is the general arrangement of what particles look like in these states of matter. Now I gotta find... There we go. Now, if we were going to use language to describe the observations that we can make about these states, we would use the following. In our solid right here, if you were to shake this around, it would remain cubic shaped. So what we would do is we would say that the shape of the object that is a solid is fixed. Now, if something has a fixed shape, it also has a fixed volume. You cannot change the volume of something and keep its shape exactly the same. That's just physically impossible. For a liquid, if I were to measure the volume on my flask, we'll say 20 milliliters or whatever, and then I were to pour this into another container with, like, say, a graduated cylinder. Okay, now it's a flask because I drew it crooked. And this was the 20 milliliter mark. Then pouring this quantity of liquid would actually fill it all the way up to the same spot, despite the fact that the shape of it is different. Liquids can have whatever the shape of their container is. And since all the containers in the world have different shapes, we would say that the shapes are variable. But their volume will always be whatever their volume is. If you pour 20 milliliters of water into a cup, and then you pour 20 milliliters of water onto the ground, they have different shapes, but they're still 20 milliliters of water. Lastly, for a gas, gases have variable shape and volume because gases always expand to fill their container. Oh, we should do that. Gas equals container size. So if I were to uncork the gas would escape, and then it would be the size of its new container, which if the room was sealed, it would be the room that is around the flask. Or if this was outside, the new room would be the atmosphere. All right. Now, some more definitions of these terms that we used earlier. Mass and volume. Right here. For mass, we have an important distinction to make. Because the amount of stuff in something and the amount of force that is exerted by that something in a gravitational field are related, but are not the same thing. If you've ever taken a physics class, you might have heard of this expression. This is Newton's first law, right? Force equals mass times acceleration. You are currently undergoing acceleration right now. It's just that there is a force that is preventing you from doing that, which is the ground or the chair that you're sitting in or whatever. Gravity is an acceleration. Due to all matter being attracted to all other matter, and the Earth being the biggest matter around us, we are attracted to the Earth at a constant rate of 9.8 meters per second squared. We have a mass that is associated with us, which is how many kilograms we are, and those two things together make a force. Another term for force is weight. So when you go to the scale in your bathroom or your doctor's office or whatever, and you stand on it, what you are actually doing is you are exerting a force down onto the scale, and the scale measures that. That is printed out as your weight. We're actually not going to use the gravitational constant, like, at all. So you don't have to worry about that. I use 9.8, but depending on the application, it would be more or less sig figs. Now, the only reason that I'm bringing all of this up is because the word that we use when I say go and figure out how much mass something is I use the term weigh it. Like, go weigh it. Not weigh it as in I don't know how to pronounce weight. I looked at that and I was like, oh, wait a second. Yeah. So, you're going to weigh things, and in doing that, you will determine their mass. Because what the balance does is it says, oh, okay, I see its weight. I'm going to divide by acceleration. And then whatever result that I get must be mass, because the acceleration is presumably constant, which it is. Okay? So mass is how much matter you have. Weight is your matter times gravity. Okay? So be careful. Here's a visual example. If you're standing on Earth, your mass might be 100 kilograms, and so your weight would be your mass times the gravitational constant, which would be 980 newtons, which you could convert to pounds. But if you go to the moon, the gravitational constant on the moon is much, much lower because it's much less massive. So your weight on the moon is much, 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 much less, but your mass is the same. Your mass is always constant no matter where in the universe you are. This is why we care about mass in kilograms over, say, weight in pounds, because pounds are force, but kilograms are mass. They're different units, and they're used for different things. Okay? All right. Now, something interesting happens when we do reactions with chemistry in terms of their physical properties. One of the first observations that was made was by chemists who would do reactions in sealed jars. So they'd put a bunch of stuff into a giant glass sphere or something, or a box that was sealed shut, and then they would hit a button to ignite a sample, and then they would take the entire container and then weigh it. And what they observed was that whenever a chemical reaction is done in a closed environment, the amount of matter that's there is always constant. And so this is known as what's called the law of conservation of mass. Now, you probably remember that word law. What does a law mean? Well, it describes a bunch of situations, but doesn't tell you why, right? Why is matter conserved in a reaction? Well, for a law, you would just say, well, whatever you put in must be what comes out. But in terms of like nitty-gritty details at the atomic level, that's a little bit more difficult. So it's a law, it's not a theory. It doesn't explain why this happens, it explains what is going on. Remember that? That'll come up on exam 1, so make sure that you don't forget all your chapter 1 stuff. So here's a great example here. Everybody loves beer. I realize that half of you are probably high school students, so you don't get to love beer yet. That's too bad. But if you make beer, what you actually do is you put a solution of like flavors and hops and stuff in there, and then you put a carbohydrate and you put some yeast. And what the yeast does is it decomposes the carbohydrate into ethanol and CO2. And then what we do is we drink the ethanol, and the CO2 gives it a more acidic sort of taste. And generally speaking, you drink it and you enjoy the flavor and you buy more of it, I guess. I don't know. Something like that. I like beer. Beer's good. But what's interesting to note is because the bottle is closed at the top here, I guess that's fine right here. What this means is that all of this process is occurring while the bottle is closed and nothing can escape. And so all of this gas that's formed, all this carbonation, some of it ends up in this headspace up here. But most of it ends up in the beer itself. If you were to weigh the bottle before and after the fermentation process is completed, you would get the same result. They would have the same mass, because the bottle's sealed, of course, right? Let's look at an actual example of this. So if I have Alka-Seltzer and I put it in water, it starts fizzing. And this is an experiment that they do at Seattle Community College. When I was teaching there a long time ago, they would have you'd weigh a glass of water and weigh a Alka-Seltzer tablet together. And then you would drop one in the other, and you would weigh the tablet and water mixture after all the gas had been given off. And you'd notice, oh wait, the numbers are different. So let's suppose that I have a 10-gram Alka-Seltzer tablet, and I add it to 50 grams of water. And when I weigh everything, this is the number I get. And you might think, oh, the conservation of mass isn't working here. Well, what happened? Yeah, it's open, right? So all these bubbles that are in here, they just kind of escape into the atmosphere. And then they're just gone. Gone forever. I can't help you there, Kyle. I'm not a tech expert. So, okay, if the gas escaped and the final mass of the solution is 57.9, what was the mass of the gas that was in there? How much CO2 was in the container? And by extension, how much CO2 was in the Alka-Seltzer tablet? How would I get that information out of these numbers? $2.1 is right. How did you get that number? Yeah, so you add these together. Oops, that's not the pen. So this is 60 grams. And this is 57.9, so if I just subtract those two, I get 2.1. All right, so the conservation of mass is actually a really simple notion, but it's going to be very important to us later on when we start doing chemical calculations. The next thing we can talk about are some interesting properties that matter might exhibit, and so these are going to be observations that we will make using either our senses or some sort of tool. For instance, I might heat up something to a specific temperature, and then it'll melt. It'll no longer be a solid, it'll become liquid. Maybe if I heat something else, it explodes. It combusts, it scorches, it just breaks into other pieces, who knows. Other objects I can put in liquids and they'll dissolve, and if I evaporate them, I might be able to get the solid back, but sometimes I can't. And then, like we said at the beginning, I could just measure the properties of an object using a tool. So these are all things that we can do to matter. These are just examples. There are tons and tons and tons of things that you can do to matter. You can eat matter. You can draw with matter. You can throw matter. You can drive over matter. You can mix matter with hot water. Like, the list is endless. But what our objective is for this lesson is to differentiate between which actions have no effect on the matter's identity and which actions change it to what we would consider to be an irreversible adjustment. And this is going to be our rubric. If I do this to my matter, will it change irreversibly? Now, when I say the word irreversibly, what I mean is it will take great difficulty to get this back. For example, iron will rust and turn into iron 3 oxide. Iron and iron 3 oxide are different substances. One is iron, which is sturdy. The other is rust, which is brittle and orange and flaky. You can turn them back into each other, but it is very difficult for that to happen in one direction. And that is for your rust to turn back into iron. That's very difficult to do. So when I say something is irreversible, what I mean is reversing it is actually really difficult. So it's not impossible, but we're going to treat it as too much effort. Okay? So these processes that I'm going to show you will either be really easy to fix or really, really difficult to fix. For example, cooking. How do you uncook your pizza and turn it back into raw ingredients? You kind of can't, right? Because what you're doing are some chemical reactions in there. But if you make Kool-Aid and you had a really good filter, you could filter out all the sugar and dye and stuff and get the water back. So mixing stuff for Kool-Aid is something that you can undo, but cooking you could not undo. So those are more examples. We're going to look at these categorizations on these next few slides. If you dissolve a solid in liquid and don't get it back from boiling the water, then where did it go? What I mean by that is that you don't get back the original solid. For example, in the Alka-Seltzer case, since the gas evolved out of it, what you would recover would be something different than what you started with. And if you put that new solid into water, it wouldn't emit a gas. So that's a good clarification. Thank you for pointing that out. So we're going to talk about properties. A property of matter is any characteristic that distinguishes it from something else. And so what I mean by that is that you can assign a property to anything. The piece of paper in front of me is blue. That would be a property. The orc on my desk is green. That would be a property. I have a golf ball that is round and has dimples. Those are properties. These are terms that we can use to describe things that differentiate them from other things. For example, the piece of paper doesn't have dimples on it and is not round. So I can identify it by sight that, oh, that's not a golf ball. It sounds like a duh sort of statement, but it's actually really important. On the screen, I have some properties that you can make about various things. You use any sense that you have to determine properties. The other word that we're going to look at are changes. Changes are any action that causes matter to change, duh. But what will happen is the identity will appear to be different before and after. And our job is to identify if the before property and the after property are actually the same. And so over here, we have bread before, and then we have moldy bread after. Here we have iron, and then we have rust after. Are they the same? Can we undo the change in a trivial way? If we can, then they must have been the same thing, and all we did was physics, because physics is very easy to do. But if we cannot undo them, then we've done chemistry, and it's much, much harder to undo. Here's the algorithm that we're going to be using for these problems in order to determine the identity of the matter before and after some action. Now, you'll notice the word chemical formula here. The chemical formula of something is not always known, especially since we're in an introductory chemistry class. Now, some chemical formulas you actually know, so like CO2 or H2O or O2 or N2 or whatever. Now, you're going to develop this context over the course of Chemistry 140, and also as you continue through the chemistry series, you'll start to pick up like, oh, I know what that matter is. But basically what we're doing is we are looking at the identity of the matter before and after and seeing if it has changed. If it doesn't change, for example, I start with H2O, and I end with H2O, then all I've really done is move the molecules around. That's physics. And the trait that we would call that would be a physical property or change. So if you do something to your water and it remains water, at least at the molecular level, you've done physics. Water and ice are both H2O. When you put your water in the freezer, you don't do anything special to it and make it some other chemical compound. All you're doing is slowing down the movement of the water molecules so that that picture that I showed you before, let's go back to that really quickly. Oh, I didn't actually need to do this, sorry. That's why I drew it on this slide here. Remember this picture right here? If I were to slow down the temperature of something, and that's impossible to see what I'm writing because I hid it under there. There we go. If I make something colder, the speed of all of these arrows down here decreases. And if I reduce the speed to almost 0, then they become a solid. If I increase the speed, then this happens. Adding heat to something is just physics. You're increasing or decreasing the speed at which the particles in the container move. Now, let's suppose that I do a reaction with my stuff here, and that's the eraser for the pen. And this happens. I'm going to do this just so it's balanced. What I started with in this case is very different than what I ended up with. And if what you start with and what you end with are different, then what you've done is chemistry. Okay? So that is our rubric. Is it the same formula before and after? The answer is yes, you've done physics. The answer is no, you've done chemistry. Now, because this is a chemistry class, we care about the chemical reactions a little bit more. But physical processes are very common, and so we're going to involve those in our studies too. So let's look at some examples here. If I have ice, and I let it melt, and I look at the formula before and after, I observe that the formula is the same. This is because all I did was change the speed of the molecules. So we would say that melting is a physical change. The same is true for boiling. If I heat up water on the stovetop, what I'm doing is I'm giving the water so much energy that the water molecules are able to separate from each other. But they're still water molecules. They're not just H's and O's flying around. Now, how would you know that before taking this class or without like having any sort of science background? And the answer is you kind of can't know that, right? So if you're like, well, where did this come from? How do we know the formula? That's okay. There is a little bit of this process that is going to require you to just sort of take the answers on faith until we have more information. But intuitively, you should be able to determine which actions do not change the identity of the matter. For example, here's one right here. I don't know the formula of paper. In fact, paper is some complex hydrocarbon made of cellulose from a tree or another plant. What is that formula? It's like CXHYOZ or C6H5O5N or something like that. I don't actually know the formula, but does it matter? Well, what happens when you tear paper? Is it still paper or is it something else? What do you think? Also, I don't know where this person got this jaggedy piece of stuff to tear this page. Yeah, it's still paper, right? You could write on it, you could fold it, it's just smaller. So if you tear a piece of paper and you make it a smaller piece of paper, both of the pieces are still paper. They function the same, they have the same properties, so they must be the same thing. So what you've done is a physical change. But now let's suppose that instead you take your lighter and you then burn the paper into pieces. I'm doing this experiment right now. No, I'm not actually doing that. If you burn the paper what happens to the paper before and after? Are they the same? What do you think? They're definitely not the same, right? You can write on a piece of paper, but you cannot write on burned paper. It's just ash. It's all crumbly and carbonized, and it's impossible to manipulate in the same way that paper was. You can do other things with ash. For example, you could write with the ash, but you can't write on the ash. Like, you could actually use it as a source of black coloring. So, like, it could be used for paint. Or you could use it to draw. Like, charcoal drawings are definitely a thing that people do. And it's really impressive to see when it's done well. Where does charcoal come from? It comes from stuff that's been burnt. You get carbonized matter, which is charcoal. So in this case here, I had something where I didn't know the formula, and then something after where I still don't really know the formula. But they're so obviously different from each other that this must be a chemical property or change. Now, if you aren't sure, remember what we talked about at the beginning. Could I transform it back easily? In the case of water or ice melting into water, yeah, you can transform it back. You just lower its temperature. That's not hard to do. You could go outside in the winter, and that'd be enough. For paper, that's a little bit harder to do, but it's still paper at its core. So, like, if you taped it back together, it would work. You could still use it. But for paper burning into ashes and carbon and soot, the process of getting that stuff back into paper is to plant it in the ground, grow another tree, send the tree to the lumber mill, turn the tree lumber into pulp, press it into paper, and then you have paper. That's not a trivial process. And in fact, doing all of that, a lot of chemistry goes on too. Anything that's growing undergoes chemistry. So if you look at a process and you're like, shit, I don't know if that's chemical or physical because I don't really know the nature of the matter, consider how easy it is to reverse. The other consideration you can do is, can you do it again? Like, can I burn the paper a second time? No, you can't. So it must have been chemical. Can you fold paper a second time? Yes. So folding must be physical. Now, in chemistry, we're going to be writing chemical reactions like this. We're not really going to put many chemical reactions in these slides until we get to about unit 10 or so. Maybe 13, something like that. It's later on. But for now, whenever you see something that looks like this, where there's a bunch of symbols and then an arrow and a bunch more symbols, we're trying to represent chemistry. And the arrow represents a chemical change. All right, let me put a bunch of these on the screen here. What I want you to do is go over the answers in the chat with each other, and I want you to determine, is this a physical process or a chemical process for the key term in here? The key term is... it's not listed as the first word, so you're going to have to look around for some of these to figure out what object I'm speaking of in the statement. And then tell me, is it physical or chemical? Can you get it back to how it was in terms of its molecular state, or did it just never change in the first place? Okay? So talk it out with the people in the class, identify chemical or physical for each of these changes, and we'll go over the answers in just a bit. Oops, I don't know why that first comment was held, and I'm just looking at my phone. But it should be on the screen now. Now, once you've got the answers, try and justify your answer. Like, why did you select physical? Can you explain? If you type it in the chat and explain your answer, then that means that you understand what's going on, presuming you have the right answer. So go ahead and do that while the rest of the class is finishing up, and we'll do the answers in 2 more minutes. All right, let's go over the answers, and then we're going to take our break because it's about that time. So that's not the pen. That's not even what I wanted to do. All right. I'm going to boil water to make delicious pasta. I could see why YouTube might think that that's spam, but it's not. We're going to boil water to make delicious pasta. So in this situation, we are talking about the water being boiled here. Boiling is just the act of turning something from a liquid to a gas. But it is still water. So I got to get the pen to do that. There we go. We would call that a physical transformation. If I'm just looking at something, that's the wrong color. There we go. If all I'm doing is looking at it, am I changing the identity of the substance? Well, no, I'm not, right? It's still grape soda before and after. Where'd my pen go? Oh, I just have yellow, that's why. I keep changing the color of the wrong thing that I'm working with, and it's annoying me. There we go. So we would say that grape soda, simply being observed to be purple, is physical. And that would just be a physical property of it. Alright. I'm going to dissolve Alka-Seltzer in water. And when I do that, it releases a gas. Now, the releases a gas part is actually the important part of the statement. You can dissolve all sorts of things in water, but chemistry may or may not happen. You need some other accompaniment to indicate that. Now, how do I know that chemistry has happened here? And the answer is, well, we look at this part right here. Do Alka-Seltzer or water on their own release gases at room temperature under normal conditions? And when you think about that, you should come to the conclusion that, well, I don't think that they would do that. Otherwise, the container you buy Alka-Seltzer in would explode because it'd just be constantly spitting out gases. And any water that you have would just be bubbling the instant that you pour it, and it would just keep doing that. So it must be something about combining the two of them together that causes it to happen. And that is exactly what happens. Something in Alka-Seltzer changes its chemical formula when they are mixed together. Now, you're right, water may have some gas in the solution. It may have some air dissolved in it. But certainly not the quantity that you see Alka-Seltzer give off when it's mixed with water. Alright, we're going to melt sodium metal. Melting is just a physical change. So even if it is something you haven't really seen happen, if I tell you you're going to melt it, that's just physics. What about ignition? If I ignite anything, can I recover it easily? If I had a bullet and I fired it in a gun a second time, could I do it a second time? No, I can't do that, right? So this must be a chemical reaction. Gunpowder is a chemical reaction. It ignites with oxygen and produces a gas. Now, if I take air and I compress it and I put it in a scuba tank, is that a chemical or a physical change? I have air that's occupying a large volume. What is compressing? Well, I make it occupy a small volume, right? So since it's air before and air after, must be a physical change. All right. What if I whittle lumber into a sculpture? That's just like the paper example where I was cutting something into smaller pieces or tearing it. Whittling wood is just cutting the wood into tinier and tinier pieces that look like a squirrel or something, right? So it's still wood before and after. Therefore, it must be a physical change. Finally, if we combust something, just like with the ignition, that's also chemical, because the gasoline you combust, you don't get it back without great, great effort. As in, a dinosaur breathes or eats or breathes it, dies, and then is compressed over billions of years to become oil, which we then refine into gasoline. Or we go to great pain to do it ourselves. Alright. Those are the different actions that you can take with chemicals, substances, and identify those changes as either physical or chemical. We are going to take a break before we continue to the next set of categorizations. So I'm going to, oops, that's the wrong thing. Let me put the timer on. We will go back to, oh, I messed up, hold on. Trying to drag something on the screen here. We'll go back to the Final Fantasy World Map music. I'll start the clock, and I will see you in just a bit. Hello. We're back, and didn't get to Final Fantasy IX, which makes me sad. Also, someone else would like to say hi. Say hi. Now she's shy. Maya's back for some reason. There we go. I guess she has to check in on me every hour to make sure I'm still working. I don't know, and not just, like, playing Final Fantasy 15. This slide talks about a term that will occasionally come up. The terms are extensive and intensive. An extensive property is one of the properties that we talked about from earlier that depends on how much stuff you have. For example, matter is measured in mass, in kilograms. So the mass of an object is extensive. The more matter you have, the more mass it has. But intensive means that the property is independent of how much matter that they have. And so what that means is that, for example, I might have 100 grams of water and 1,000 grams of water. The masses of them are different because mass would be extensive, but their boiling point is the same. They both boil at 100 degrees Celsius. So extensive does depend on the amount of matter you have, and intensive does not depend on the amount of matter you have. We literally just talked about weight, so let's just put these examples on the screen, and I've already done boiling point. So of these 5 properties, one of which has been done for you, oops. Get the pen back here. So this is intensive. Which properties of matter are extensive and which ones are intensive? Once you think you know, type your answer into the chat. Maybe. Well, let's look at these. All right. If I pour more water, will that affect the volume? And that's kind of the rubric that I use. Is if I pour more of it, does this property change? And if it does, it's extensive. Now, of course, if you pour more water, its volume changes. But if I pour more water, is it more or less flammable? And the answer is, well, no. Water is not flammable, regardless of how much water you have. We already did mass. Now, state, okay. If I pour more water, will its state change? Does the state depend on how much stuff I have? Oh, I see. Yeah, volume for a gas would definitely be intensive. Volume for most matter, I mean. But for state, if I give you more water, it's still going to be a liquid at room temperature, right? So state is intensive. And I think that that's it. Yeah, that's it for the first section. The second section is just categorization, and the third one's here's the periodic table. So we're going to finish most of this today. All right, so let's talk about pure substances and mixture. So what we're going to do now is we're going to talk about various types of matter. Why is flammability intensive? Because if I give you gasoline, you can light it on fire. If I give you more gasoline, it's not more flammable. It's still as flammable as it was when I gave you less gasoline. The energy that you get from burning it is not intensive, though. But the fact that it is flammable or not is intensive. What we're going to do in this section is we are going to talk about mixtures and try and categorize them in ways that describe what we see. So I'm going to put 2 things on the board here. So I got a glass of water and I've got a cake. Which of these could you describe as pure? The water or the cake? Yeah, it's the water, right? You could definitely describe the water as pure. Maybe not necessarily from the picture, but you can have pure water. Can you have pure cake? If you can, let me know. I really want it. No, you can't have pure cake. Why can't you have pure cake? What property of cake prevents it from being pure? Is cake not pure sugar? I mean, we like to think that, but is it really just pure sugar? There's other stuff in there that's bad for you too, right? Like the frosting is mostly just fat. Yeah, there's a bunch of other stuff in cake, but in water, it's just water, right? So with matter, we can define these as our categories. So we can say that something is pure or a pure substance. Or we could say it's part of a mixture. So those are our two categories for all matter. We're going to take all matter and either declare this is pure, because there's only one type of substance, or this is a mixture. I can't even read that, so we're just going to delete that. Or it's a mixture, and it's all sorts of stuff mixed together. Now, whether you can unmix it or not is not the topic that we care about right now. What we care about is it mixed to begin with? Now, for the water, we're starting to get into semantics. Did I say that there was lead, copper, or fluorides in the water? Can you see them and observe them? Are you assuming they're there? Do you know where I source this water? You may be talking about your own water in this case. So be careful what assumptions you are making. Only use the information that I present to you. I gave you a glass of water and a cake. Pragmatically speaking, yeah, there might be some additive in there, but do you know what that is from just looking? No. Can't tell. We don't have that information or data available. So just use the surface information that I present to you when answering these questions. Because if I put water as one of these questions, I say, is it pure or a mixture? The answer I want you to say is pure. If you say mixture, I will mark it wrong. Because water, in the context of that question, is not a mixture. Because at some point, you could say, theoretically, there's no such thing as a pure substance. Why are we doing anything like this? Everything's always going to be a mixture, right? But this still does help us somewhat. So we want to just try and take surface level observations to categorize. And I hope that explains why we don't need to worry about ppm or ppb for these examples. Because that is going to come up on the exam, and I know people are going to be like, well, if I get water from the Puget Sound, but I take it from the surface, is it going to be a heterogeneous mixture? And yeah, it will. Or if it had like dust or sand in it. Or no, it won't if it's just water. So, like, those sorts of things can come up. And what I want you to do is just interpret them in the simplest, most common term. If you can. Here's our chart. Does the matter contain only one substance? If it does, it's a pure substance. If it doesn't, it's a mixture. On the board, I have two examples of pure substances. These substances are pure despite the fact that you might not know their identity. And so what you need to do, in some cases, is look this information up. For example, what is a diamond made of? Turns out a diamond is just carbon. What is table salt made of? It's sodium chloride. If you know these things, then that's great. You wouldn't have to look them up. But if I said, like, electrum on the quiz, you might not know what that is, and you're allowed to look that up. Like, that's the whole point of having the internet available, right? Type in electrum Wikipedia and see what it is, and you'll find out, oh, Electrum is a mixture of silver and gold, because gold is rare and silver is less rare, and it makes a really shiny thing that people like. So when you get a substance that you don't necessarily understand, but you can identify that that is the only substance, you can call it pure. From that point, we can then categorize something as being either one of two different subcategories in the pure category. So the first thing we're going to talk about is an element. An element is composed of only one type of matter. The types of matter that are available for us to make things out of are on the periodic table, which you may or may not have access to at this very instant. So what I'm going to do is I'm going to close all these quiz windows I was opening during the break, and I'm going to go www.ptable. This is the periodic table that I use most of the time. Let's see if I can window capture this. That's not a periodic table. That's my timer. There we go. Boop. I can make it a little bit bigger. I'm going to cover up the chat for just a second here. But this is ptable.com. And it provides you with a periodic table that has a bunch of information. You can hover over these elements. I couldn't read it at all. So now your message is forever deleted, and it will just sit here in the video. This is now your legacy. Congratulations. Anyway, on this table right here, you can click on any element and get more information about it. You can go to the Wikipedia article on it. You can figure out their melting points by playing with the temperature slider. And then the columns will tell you properties about it. We're going to talk about a lot of this stuff later on. But particularly what we care about for this exercise is that if your matter contains only one of these symbols in it. So like here's carbon, it's right here. My diamond has only carbon in it, so it's an element. But my table salt has sodium and chlorine in it. Since there are two elements, we're not going to call that an element. We're going to call that a compound. All right. So I will put that website in the chat here, ptable.com. That's a really good periodic table to use. The other good one is Web Elements. That's the one I've been printing out and using in class, and I actually have a laminated one right here in front of me so that when I inevitably spill water on it, it won't get destroyed. By water, I mean beer. So those are our two types of pure substances that we can have. We can have pure diamond, which is an example of an element. You could have pure, say, aluminum, which would be aluminum. You could have pure sodium, etc. And then we have compounds. Compounds have two or more elements in them. So sodium chloride is table salt, is a compound. Sugar would be a compound. It contains carbon and hydrogen and oxygen. What else would be a compound? Rubbing alcohol would be a compound because it contains carbon and hydrogen and oxygen. Sand would be a compound because it contains silicon and oxygen, and so on. Oh, I missed your question up there. I only read because they don't interact with other elements. And yeah, so they're called the noble gases. I call them noble gases because, like all nobility, they sit on their asses and do nothing. That's just my personal take on it. All right. So there are elements and compounds. We're going to treat those two categories as separate because they go with pure. Now we're going to go over to mixtures and give them two categories as well. And then at the end of all this, we're going to try and put something into one of each of those four subcategories. So the four primary subcategories will be element and compound. And then on the next slide, there'll be homogeneous mixture and heterogeneous mixture. On the screen, I have two different, I was going to say condiments, but the salad dressing really isn't a condiment. I got ketchup and Italian salad dressing. Let's suppose that you were going to split the contents of this randomly into thirds. It could be kombucha. I don't actually know. Let's suppose that you were going to split each of these into thirds. So I'm going to just randomly split this into thirds. I'm going to say this top layer, and then the middle layer, and then the bottom layer, which you can't really see. And then I'm going to do the same thing here. Which of these has all three layers the same? And which of these doesn't have all three layers the same because the solution is not the same throughout? Right, the ketchup does, right? Apparently that turned into lawyers. Oh, come on, pen. There we go. So all the layers are identical. Whereas down here, my layers are unique. On the bottom of that Italian seasoning, kombucha, whatever, I have all the herbs and all the seasonings, and you can see that it's darker. There's like a solid, pulpy stuff down there. That's the good stuff, right? On the top, it's most of the oil, which gives it the... it makes your salad not dry, is the best description that I could say. So, how are we going to categorize these? Our first description is going to be for anything that has all portions identical. We're going to call that a homogeneous mixture. Something is homogeneous if it is the same throughout. What is that? I'm not sure what you're referring to. This down here, I think this is salad dressing, but I'm not sure. Oops. That's not what I meant to do. So homogeneous mixture or homogeneous solution will have a constant composition throughout its entirety. A heterogeneous mixture will have portions that are unique. The way that I like to think of this is if you were to pour or cut or separate the thing that you are working to into distinct portions, could you choose one randomly and get the same result? For example, if you took air from your room and put it into 4 bottles, and maybe you held the bottles in different corners of the room, would they all contain the same amount of air? And would they contain the same composition of air? And if the answer is yes, you have a homogeneous mixture. If you put your substance into 4 different containers and they are unique in any way, then you have heterogeneous. For example, the top of the solution up here is mostly oil and the bottom down here is mostly solid. So if I took the bottom solution and the top solution, they would be very different, and so that must be heterogeneous. Oops. Now, there is some leeway. I'm going to try and give you examples that are obvious. For example, I might say muddy water. If I give you muddy water, the mud's going to settle to the bottom because that's what mud does. Therefore, if I were to take a scoop out of the bottom and a scoop out of the top might have a little tiny bit of mud floating around, but the bottom will have much, much more. So that would be an example of a heterogeneous solution. I might say, what about like milk? Now, if you are drinking skim milk, then it's pretty homogeneous. More or less, the entire thing is the same. But if you're drinking 4% milk or 2% milk or whatever, and you have like that little skim of fat at the top, then that would be heterogeneous, right? So I'm not going to ask you things like milk or what about blood? Like what about the plasma that you can separate from blood? So there's some leeway here. And we're going to avoid the edge cases where it gets confusing. Like, is this a mixture? I don't know. Is it homogeneous or heterogeneous? If it looks homogeneous with your eyes, we're going to call it a homogeneous mixture. And that's going to be our rubric. We're not going to worry about down at the atomic level that, oh, there's one more molecule of vinegar in my ketchup in this part than the other one. Again, we're going to try and keep this surface level. And to answer that, I believe that question about the quiz was answered there. Always use the rules for sig figs on the quiz questions. I don't know what that word is. I don't know if that's a typo or a joke. There's our chart. Here are the 4 categories that we're going to care about. So your job is going to be, I give you a matter. Like I might say a penny made before 1980, which would just mean that it is entirely copper. So if I said a copper penny, and you'd say, okay, well, it only has one substance, that's copper. And of those substances, there's only one element off the periodic table. There you go. That'd be the answer. Or maybe I said, I don't know. How about apple juice? But the apple juice doesn't have like any pulp or anything in it. So if I were to do apple juice, well, there's water and then there's apple flavoring and then there's stuff in there. So it's definitely a mixture. But are all the portions of the apple juice container the same? Well, if there's no pulp, I should put that. Then yeah, they're all the same. Sand and marbles in a jar would be heterogeneous because you could get a different amount of sand versus marble. If you had gravel, well, actually that example is coming up on the next slide here. But anyway, there's some more examples of that. And so now this is the part where I set you loose and I have you separate them on your own. So I want you to put these into one of the 4 categories. The first thing you want to do with these, obviously, is you want to figure out which side you are going on, and then decide from there which category you're going to put it into. Don't do something like this. Oh, it's a pure substance, and it's a homogeneous mixture. Don't do that. You can't have something be pure and homogeneous, because they're not on the same side, okay? All right. There's the list of things. I'll give you about 5 minutes to go over the answers with each other in the chat. And then we'll go over the answers together. And then I believe that that's more or less the last bit of the slides that we have to do. Okay, so see you in a bit. So remember that the thing that I mention is what's there. Okay? If I intended for it to be diluted nail polish remover, I would have said nail polish remover diluted with water. When I say Red Bull, I mean whatever Red Bull is sold as, and not I poured it into a glass with ice, for example. So, again, interpret the statements literally, as in what is written is the only thing in the problem. All right, 2 more minutes, we'll go over the answers. All right, let's go over the answers really quickly. Not in blue, because I want that to stand out a little bit more. Let's do red. All right. Red Bull energy drink. Let's suppose I had a can of Red Bull and I open it up and I pour it into 2 shot glasses, for example. Could you tell the difference between them? Because we know Red Bull's a mixture, right? You look on the ingredients and you see that there are a bunch of things. What is my favorite pizza spot? We'll get to that when I get to that question. Well, since they would be indistinguishable for your drinks, we would say that the mixture that is formed must be homogeneous. And most good drinks are, although things like orange juice are good, but the pulp at the bottom changes the texture and would make it heterogeneous. All right. We got nail polish remover. Nail polish remover is acetone. That's what this is. Now, because this is the only thing listed in the statement, that must be the only thing that's present. So that means it's pure, but there's more than one type of element here. There's a C and an H and an O. So this is a compound. I actually really don't like Red Bull. I can't stand energy drinks because they just taste like sadness and anger. Nail polish is not heterogeneous because there is only one substance listed. If I said nail polish remover and then listed ingredients, then it would be a mixture. For this third one, we have a bunch of stuff in my gravel, since you might not know what gravel is, right? So let's suppose I have sand, rock, and salt, and it's poorly mixed. If it's poorly mixed, that means I could take 3 scoops of it, and I'd get a different result each time. One might be more sand, and the other one might be more rock, and I don't really know why salt is in there. Maybe to melt stuff, I don't know. In any case, heterogeneous. I was going to put mix, but then I immediately started that word again, so there we go. How about nitrogen gas? If I have a balloon that contains nitrogen gas, well, it's pure because this is the only thing that's in it. Oops. My tablet is... I gotta find the right angle to tilt it at. Let's see here. Yeah, that's a little better. Nitrogen is only one element off that periodic table. We're going to call it an element. Pizza from your favorite place. It doesn't matter where your pizza is from. Every bite of... I can't spell anymore. Heterogeneous. Every bite of pizza that you take is not only delicious, but also different. The crust is going to be different from the middle, for example. Where is my favorite pizza place? Oh, Zeke's. Zeke's Pizza is my favorite, for sure. I mean, I'm not super picky. I love pizza. But by far, my favorite is Zeke's. I always order the Dragon, which is pepperoni, Italian sausage, garlic, jalapeno, and whatever herbs and seasonings they do. I haven't. Not sure where Fultano's is. I live in Everett, so if it's down south in Seattle, then obviously there's not really much reason for me to drive down there right now because quarantine and pandemic. But locally, Zeke's in Linwood is close enough that I will go get it. It's an organ. That would explain it. If I'm going for like cheapo pizza, I would say Mod Pizza is probably the best fast pizza. And Papa Murphy's Take and Bake is not beneath me. Brooklyn Brothers is just okay. It wasn't super exciting. Like I've gone there like 2 or 3 times, and every time I was like, I would eat here again, but I'm not super thrilled about it. Let's do these last 2 here. Iron metal. I only listed iron, so that's going to be an element. But over here, I list... Oh, my goodness. Now I'm not working with the tilt of my pad. Over here, I listed a bunch of elements. And I used the wrong pen for that. What the heck does that mean? Does that mean that there's a formula? Well, if there's a formula, I would have listed a formula. I did try Lombardo's. They were pretty good. What is meant by this collection of elements here? Well, let's think about how steel is made. In order to make steel, you heat up all the elements till they're molten, and then you chuck them in the bin. You mix them together, and then you let it cool. Well, the word mix there should definitely tell you that this is some sort of mixture. Now, let's think about the result of this process. If I have steel, and my steel is cut into several pieces, would all of those pieces be the same, or would some of them be like, oh, this steel is crappy steel, don't build on this one? And the answer to that is no. If you forged your steel by mixing everything with the same ingredients, they would all be equal, and then you could use them as steel bars or girders or whatever. So, the conclusion that we get is that steel is actually a homogeneous mixture. Steel is what is known as an alloy. And all alloys are homogeneous mixtures. By definition, when you make an alloy, the process that you're following is you mix it all together while it's molten, then you let it cool, and the resulting homogeneous mixture has cooled into a solid. You can still have a mixture that's a solid. All right, where are we at for time? I have 8 minutes. I think I can do the last bit in 8 minutes because there's not really much here. All right. All of those elements on the periodic table that I showed you when I referred to p-table come from a very specific place in the universe. And the answer to that is actually shown in this video that I am not allowed to play because I will absolutely get a copyright strike. But I'm going to click on it anyway. And I messed up. Hold on. You can't hear what's going on here. There we go. But if you've ever seen this video before...
How did this happen?
How did all of this happen? Where did all of these atoms come from? I'm going to post that link in the chat because this is a video that everybody should watch. You absolutely could make a religion out of that. No, don't! This is probably one of my favorite videos ever. And I can't play the whole thing because, one, it's 20 minutes long. But the introduction of the video, like the first 4 or 5 minutes or so, is chemistry. And then you proceed to biology, and then you proceed to whatever. And it's super interesting to watch and see. But where did all of this matter come from? Well, it came from the stars. Hydrogen is the simplest element, and by combining all of the other hydrogen atoms out there, you could get bigger and bigger and bigger, progressively larger elements. Excuse me. How do we represent these elements in an easy way? Well, because there are 118 different types of elements that we've discovered so far, we need to be able to categorize them uniquely. And so what we're going to do is use symbols. On p-table, and let me go back to p-table here. I want this one. There we go. Back on p-table here, you'll see that all of the elements have a 1 or 2 letter code that you can identify as shown. The 2-letter codes are always written, first letter is capitalized, second letter is lowercase. So this is CL, not CI. Okay? Be careful of that. When you're writing elemental symbols, or chemical symbols as they're known, most of the time they are the first 2 letters, or the first 1 letter of the thing you're talking about, but not always. There is an H in chlorine, believe it or not. The H is silent, I guess, but we don't write it. There's all of our elements on the periodic table. This is the web elements version. There are some elements on here that you need to watch out for because their identity is ambiguous and also Latin. So, for example, potassium right here is K because the Latin word for potassium was calcium. But P over here is phosphorus, and this is a great one that people get mixed up all the time. Don't forget that K is potassium, and don't say, oh, potassium is P. No, it's phosphorus. Here's another one. Tin is not Ti. That's titanium. Tin is over here. That's Sn. Because, again, Latin. And I don't know the number of elements that have a C in them. So there's Ca, Cs, Cr, Co, Cu, C, Cl, Ce, Cm, Cf. It just goes on and on and on forever. So there are a lot of C's in there. Be careful. But again, you're always going to have this periodic table handy. So what I would recommend is in whatever folder you are saving for class resources and stuff like that, bookmark p-table, and then just open it up before the quiz. And just have it there, because you're going to need it from now on. Finally, the last thing we'll talk about today is the chemical formula of a substance, which we've already talked about earlier on in the class. The chemical formula just tells you the arrangement of atoms in a molecule. Well, it doesn't tell you the arrangement. It tells you what atoms are in the molecule. And it tries to give you some indication about the arrangement, depending on how it's written. So, for example, water is 1 oxygen per 2 hydrogens. We write H2O. We're going to talk about why we put H first later on. For now, just write them in the order that you see them. When you write formulas, you do not indicate a number if there is only one. So right here, don't do that. During a quiz, you may switch tabs, you may open a new browser window, you may consult your phone, you may go to the bathroom. I don't give a shit. You can do whatever you want, but you have to finish before the time is up. That's the only constraint. You can ask anybody any information you want, but remember, you only have 30 minutes. So if you want to have your dad or your brother or your uncle or whoever do the quiz for you, they better be really close by. You better not have to run next door and write all the problems down because they don't have internet or whatever. Like, that would not be a good strategy. Ideally, I hope that you would be the one that knows how to do the problems. And that's why I've set the time limit so low, is because the easiest way to do these problems is for you to be the one doing them and already know how to do them, and not have to look everything up. But you can do whatever you want to. Other issues that can come up: don't do what I call lower caps. So if you write this, if you're one of those people that writes only in capital letters, you need to fix that for chemistry, because writing this is wrong. What's important to realize about chemical symbols is that when I write this, this is a universal symbol. It'd be like if I represented it as, this is the symbol for iron. It's not. That's the symbol for earth. And then somebody else said, well, I'm going to just draw the triangle and the line. I don't need to really draw the whole big triangle. These are different and represent different things in the same way that these are different. And that might sound like semantics and being really pedantic about what we are doing here, but the reason that it's universal is because we have established a standard. If I go to Japan and I want to communicate with chemistry, the scientists in Japan would understand what capital F, lowercase e means, because everybody uses these Roman characters for elemental symbols. But if I showed them capital F, capital E, they might not understand what that is, because that's not the chemical symbol, okay? So you got to make sure that you write them in the correct notation, where the first letter is always capitalized and the second letter is always lowercase for an elemental symbol. The second thing that's going to come up later on is that we have parentheses around polyatomic ions, which we showed at the beginning of the class. When you have polyatomic ions, you must use parentheses, so that you don't end up in a situation like this, because later on we'll see why that can be wrong. And I think that that's it. Yeah, we don't need to do this example because it's literally just counting all the atoms. You can do this on your own time, because I think we're at, yeah, it's exactly 4. So we're going to go straight to the happy work. All right, and that's Unit 6. Unit 6 is real short. Quiz number 3 involves Units 4, 5, and 6. It will be posted tonight. Quiz number 2 will have last call. I'm going to say last call is around midnight or so, because a student asked me for that over an email. So happy to do that. I'm going to close the quiz at midnight, maybe a little later if something comes up. Make sure that you get your quizzes in by midnight tonight. Once the quiz is closed, it will say closed, and then you will be able to see the key once you click on it. At that point, you may ask me any questions that you'd like, but I cannot answer any questions about Quiz 2 until that point, and I do apologize. There is an exam coming up soon in week 6, which means that one of your quizzes coming up soon will have a shorter deadline than a week. Quiz number 3 is due next week, just like all the other quizzes. You get 1 week to do it. So a quiz coming up soon, though, will have a deadline that is not a week long. The deadline will instead be Friday or Saturday, so that you can then have Saturday, Sunday, whatever, to prepare and study for the exam on Monday. All right, I want to thank everybody for watching. When we come back on Wednesday tomorrow, we're going to discuss lab number 2. I will see you for that. Have a wonderful rest of your evening. And stay safe, stay healthy, stay at home.